provide a good presentation. Our project is floating offshore wind turbines, coupled dynamics, math modeling and experimental verification. Thank you to our project supervisor, Dr. Shai, Mr. Kolu, and PhD researcher, Michael Bodge. This is my team, and these are the tasks which led to a successful design and manufacturing of our model. And I will lead you through the introduction, the aims and the objectives, and we will take you through the whole process of manufacturing this model. Right, why floating offshore wind turbines? Because as we move into much more deeper offshore environment where we can extract more wind energy, and as we cannot have monopile or jacket structures beyond certain depth, the solution is floating offshore wind turbines. Another question, why floating offshore vertical axis? Why not horizontal? Vertical axis is cheaper to manufacture. Dynamics is quite simple. You can have straight blades. Its center of gravity is lighter, it's lower, and it's quite easy to have a vertical axis than horizontal. The economic viability is better on vertical axis. You can see the dynamics involved on vertical axis floating wind turbine, aero, hydro, control, structural. All these forces coupled together on a vertical axis wind turbine. It's a huge challenge and a very new research area. Hence, we decided to take on this challenge. One of the main objectives of our project is to take this numerical model built by PhD researcher Michael Bodge and validate it by an experiment, and hence the name of the project floating wind turbine coupled dynamics math modeling, which is hydro and aero, and for experimental verification. Moving on, if we need to validate this model experimentally, there are certain challenges associated with it. The first one, we can't build a full-scale prototype. It's really expensive and it's too big. Even if we build a subscale model, there are scaling issues. Aero scales with Reynolds, hydro scales with Fruderon. Even if we do build a subscale model, it requires a very, very big facility, like shown in the video. And unfortunately, we cannot accommodate that in our Oceans lab. So we had to come up with a solution to come up with that. We thought we will build a prototype which will simulate the air loads. But let me start. We'll take a full-scale model. We had this pod already, and we will simulate the overturning moments on a full-scale model first. Then we will subscale it down, and we'll simulate the similar overturning moments which we achieved from a full-scale, and then subscale. Now, we already had this pod, which was built last year by an MSc student, Graziano. He's already tested this pod. This is our floating structure. So we started our design from the base, and eventually we built a physical model which will simulate the aerodynamic loads. And ideally, the project was to perform the experiments as well, but unfortunately, because of the time constraints, we were unable to do that. But we have built it, and one of us will carry on further with the experimentation. I'll pass you on to Kadir, who will go through with the subscaling process.
Thank you, Harshal. Yes, starting from the point that we have already pods. So we had the 3 megawatts full-scale wind turbine for a start, and then we subscale by using the 1/50. Then we get the values of the subscales. So then those values can be used for our experimental models dimension to extract our experimental model dimensions. So what was those values that we needed to extract is the 7 characteristics, which was from the center of gravity, total mass, overturning moments, inertia forces, and gyroscopic forces. And then using the equations that we created with my colleagues Tristan and Akhil, we extracted those values by them. And we also subscaled from the full-scale wind turbine as a 16 RPM to the subscale to the 113 RPM to simulate the same aerodynamic loads.
As Julia mentioned, there's 7 characteristics of the turbine which we need to replicate in our model. Most important are the overturning moments. This is just a general view of what the overturning moments look like. The way you can do this is just by spinning a mass, simply like This produces the overturning moments we need, but unfortunately the centre of gravity is offset, so this wasn't, we couldn't do this. So we added a second mass. Because of the difference in height, we still have the overturning moments, and the centre of gravity is in the centre as we needed. So we had 7 characteristics which we needed to equate, and to do this we had 7 variables: height of the top arm, height of the bottom arm, length of the arm, radius of the arm, radius of the shaft, radius of the mass, and the length of the mass. Hopefully, with these 7 variables, we would be able to satisfy the 7 characteristics. We then looked at the limitations of the problem. So we had limited materials from the workshop, so we weren't able to vary the shaft or the diameter of the arms. Also, the ocean lab, there was a maximum size, so we had limits on the height that our model could be. So we ended up with 4 variables, 7 equations calculated for the 7 characteristics of the model, and we had to equate these with the subscale values that Kadir had worked out. Used a random approximation method, so generated a million sets of the variables within the limits we'd set, so like the height of the ocean lab. We then subbed these values into the 7 equations for the model and equated that to the values we needed to produce. We then found out the percentage error on each equation, added them up, searched for the lowest percentage error, and then from there we could extract the values, the 4 variables that we needed. With the constraints, we quickly realised that we weren't able to satisfy all the equations, so we had to concentrate on the most important ones, which were the overturning moments and the centre of gravity. We noticed that the centre of gravity was quite low, hence the big mass we've added on the top there. And also, with our final results, we didn't accurately produce IXX and IYY, but this shouldn't be a problem as this can be inputted into the model we're trying to validate. This is just a view of the final dimensions we got. Now hand you to Kadir, who's used the cat.
Okay. Thank you, Tristan. My job was to design the CAD model through Tristan's and Kadir's work, which numerically satisfied our equations. We were able to now physically sort of look at how to build this. So initially there was a few, we needed these certain components like the pod, a housing, the shaft and arms, the masses that will spin, a motor, and the weight at the top for the center of gravity and IX and IO. This is just a general exploded view of what the CAD looks like before it's assembled. There's a few design constraints. Initially, the base of the pod is quite thin, it's only 4 mil. So to drill holes in there would be, you'd risk its stability, I guess. And therefore, what we decided was to glue the pod, the pod to the housing. The lid of the housing is also, it's removable, so we can place the motor inside. The motor is then fixed onto the lid via the fixing holes, and the lid onto the housing via clips on the sides of the holes. The shaft is then fixed onto the motor through a tapered hole, which is also threaded to give it the extra rigidity. The arms are then made, the masses were made hollow, so to make the design sort of adjustable, so you can adjust the mass, therefore adjusting the moments and forces that are created. These are attached by a pin, as you can see from here, hopefully. The mass is then screwed onto the top of the shaft. I know it looks like there are pins here, but just don't listen to yourself. It's actually screwed on, and thank you. This is just a model of how it works. Actually, there's a problem with the motor because it wasn't waterproof. So, because this is going in the water, the housing had to be made completely sealed. So, there's one ventilation hole which is used as a cabling hole. There's silicone glue around the housing for extra water splashes. And during experiments, you might consider a thin plastic film in case of extra splash. But yes, thank you. I'll pass it on to Farid.
Thank you, Akhil. I am Farid Alshihri. Good afternoon, everybody. I'm going to speak about the final movement analysis for our model. First of all, when the CAD file has been imported into Abacus, the following material has been assigned. The aluminum material for the shaft arms and waterproof box, and wood for the pod, and steel for the spinning masses. And we assigned the elasticity properties for every material and density. After that, after doing the steps and sections for every part of our model, we applied two centrifugal forces as a load and one torque. The centrifugal force equal mass multiplied by omega squared multiplied by the length of the arm, which is equal 23.9 at 120 rpm. And the torque equal 0.79 Newton meter. And after that, we did the boundary condition and we constrained the model from the bottom. As a result, this graph show or illustrates the maximum displacement at the top of the shaft, which is equal 7.4 millimeter. And this illustrates the maximum stress, which is on the the base of the pod around this area. The maximum stress equal minus 1.38. And to conclude regarding to finite element analysis, the high stress around the model because the material of the pod and because the pod has 4 millimeter thickness of wood and the highest displacement at the top of the shaft because the centrifugal force, and all stresses are in acceptable limit between minus 1.38 and 1.56. Thank you for your attention. Now turning to hydrodynamics with ours.
Good afternoon, everybody. I'm Amrutraj, and I'll be taking over the hydrodynamics. This was the pod which was available for us, and it was built by Graziano Spano last year. Taking this into account, I just built a Genie model on CSAM. Now the CSAM, the Genie model requires only 1/4 of a pod because when we input it into the hydro D for analysis, we can replicate it because of the symmetry on the on two axes. So only 1/4 of the pod is enough if it's built, and we can save the computational power also. This model was built for both the full scale structure and also the subscale structure for comparison. The maximum angle of inclination the pod will encounter was calculated because there will be waves and there will be oscillation of the pod. Hence, the maximum angle that was calculated to be 14 degrees. That's a crude diagram on Abacus just to show the maximum angle. This is a comparison between the values obtained by Graziano Spano and our model. Now, Graziano Spano, he never had this structure at the top of the turbine, on the top of the pod. There was just water in that. Hence, there is a difference in values. The red one is the model that was built by Spano, and the subscale, the model rotating moments are shown in the blue line. This is a comparison as values now. Okay, but this is a comparison which shows the maximum angle actually for at the overturning moment that was calculated for the full scale structure. The maximum angle goes up to 9.026 degrees, and for and for the subscale edition, it is 9.085. That is the exact values which are shown, which are not shown here actually. And this is the comparison between the experimental and the subscale edition. Because there were some constraints present in our model, the constraint of the workshop and the constraint of the ocean lab, we had to come up with a few modifications for our design. Because of that, there was difference in the angle of inclination. The maximum angle of inclination, which was found out for this pod to be 8.6 degrees, whereas the model which we actually subscaled from the full scale version was 9.026 degrees. Thank you very much.
Okay. After mathematically getting the dimensions from MATLAB, making the design, CAD design in Pro Engineer, doing FEA analysis in Abacus, and doing the stability analysis in Hydro D in Genie model, we finally started to build this model and think about how to construct it and liaise with School of Engineering workshop. Well, basically there are some challenges associated when you have a CAD model and your design and your dimensions, and then the constraints which were imposed on us from the workshop for the materials. There were certain challenges like how the concept started building up for building this this aluminum casing, because how it will, remember the pod, this pod was designed from a last year student for a cultivation and had inside, the base isn't that strong. It's got only 4mm plywood over here. So we had a challenge to design something, come up with a casing with good strength so that it can take the centrifugal and the overturning or the forces which will act when this will be rotating at 113 RPM. So we decided on a casing of aluminium, a square section, a simple section, and how we will put the motor inside it. And this connection over here between the shaft and the motor was one of the most crucial, and it took us a little while before we can agree on it, because it leads to deflection on the top of the shaft once it starts rotating at 113 RPM. The other challenges associated were total mass, as the total mass of the model, just the rotating mass model, had to be under 5 kilograms. So and then again, the workshop had certain materials like the shaft and the arms. The dimensions were fixed, so we had to liaise back to Tristan and Kadir to make sure they make the changes and the characteristics which we wanted to resolve were reduced, and finally we had to just come up with a plan to just build this model with only satisfying center of gravity and overturning moments, which ideally are quite important for the experimental validation. Instrumentation, just a couple of things: how we were going to power the DC motor, and the gyrometer, which will be placed over here, which will be measuring the displacement. But I'll take you on to the next stage, which is the motor, which is one of the most important component of this whole experiment, because the motor will provide the torque for the shaft on the arms and the masses to rotate at 113 RPM to simulate the overturning moments which you will have at a full scale and will help us to validate the numerical model built by Amrutraj. So the calculation to size the motor starts from F is equal to ma, which is used for linear acceleration. To get angular acceleration, the formula is for torque is moment of inertia into angular acceleration. To reach from 0 to 120 RPM in 1 minute, the acceleration required is omega minus 0, because we're going from 0 to 12.566 radians per second divided by 60 seconds. So this was the acceleration. The moment of inertia of the arms, the masses, and the rotating shaft was 0.476. So the net torque calculated was substantially low, but there was a certain criteria about mass, as I mentioned earlier. The total mass had to be under 5 kilograms. Considering the arms, shaft, and the masses, the motor had to be under 1 kilogram. So finally we found a motor which was just 529 grams. It had really high torque, but we were quite happy with it. The drag force which was calculated was very minimal, below this, so which was quite okay to go ahead and source this motor from China. Thank you to our department as well. So it was very quick, and we got this motor in 5 working days. So build this down. Finally, once the motor was received from China, we did a benchmark testing. Thank you to Dr. Luke for this. We went to the electrical lab and tested this motor, and we found, as predicted, the voltage and RPM relationship is quite linear. The RPM we need to get to simulate the overturning moment is 113. The motor is sized to 200 RPM with 24 volt limit. So we achieved 113 RPM at 14 volts approximately without any load. It's a free spinning shaft. So we're hoping that approximately at 15 or 16 we can simulate with the top load we have. And hence the motor is good. These are some CAD drawings which we sent to the workshop and liaised with them to manufacture this model successfully. Special thanks to our supervisors, Dr. Flora, Luke, Faye, Ian Hicken, the workshop manager, and Derek Brown, who's the workshop engineer, who worked for us for this model till 1:50 today. So this model was built today at 1:47. So this is it, and we welcome your questions. Thank you very much.
How much you owe him?